Welcome to the Network Fundamentals Chapter 5 lecture on the network layer. Today we're going to talk about layer 3 of the OSI model, which is the network layer. This is a layer directly below the transport layer and above the data link layer. It is analogous to the internet layer on the TCPIP model. Now, what we're going to do is we're going to talk about the networking layer as it relates to path determination, how you find your way through a network. We're going to talk about how it relates to logical addressing. Now, we've already talked about a couple items in terms of addressing. One thing at layer 4, the transport layer, we talked about port numbers, and we talked about how port numbers were used to keep up with TCP sessions or UDP sessions between hosts. So you could say that port numbers are actually layer 4 addressing. Layer 3 addressing deals with logical addressing, which is IP addresses, IPX addresses, mainly now just IP addresses since IPX has gone the way of the dinosaur. But there are logical addresses that are assigned to a host that allow you to have connectivity between it. At the data link layer, which is one layer below the network layer, layer 2, you have physical addresses, and these are typically MAC addresses on an Ethernet network that are used to keep up with the individual host on an Ethernet network. Now, as we look at this particular layout of the OSI model, remember that at layer 7 down to layer 1, layer 7 tends to be implemented all in software, and as you move down the OSI model, it becomes more hardware-based. The physical layer obviously deals completely with hardware. The network layer is kind of that layer in between software and hardware. It's still pretty much implemented completely in software, but directly below it at the data link layer, we'll talk more about how the OSI model deals with hardware-based items. Now, here's a great slide showing the encapsulation process. One thing to notice when this happens, you have data between the host 32.11 and 36.5. Look how quickly they kind of bypass, application presentation and session layers, it's just data, and they pass it down to the transport layer, where they will then add a header, and in this header will be items such as, if it's TCP, source port, destination port, sequence numbers, window size, those types of things. It then is moved down to the network layer where it's encapsulated with a network header, and this in the world of TCP/IP is where we're going to put source and destination IP address, items such as header type or header length, all these different items that make up the the IP header. We'll then pass it down to layer 2. This packet becomes data for layer 2, and we'll put our frame header on it with source and destination MAC addresses and a CRC. And then we'll push it out on the layer 1 and make it bits, ones and zeros, go across, and it will be de-encapsulated on the way back up at the receiving host. So this is a good reminder to your students of what's happening during the communication process between a sending host and a receiving host. Now, what are some network layer protocols? IP version 4, the one that we now currently use, 32-bit addresses, usually in a dotted decimal format. IPv6, 128-bit addresses, much more important now as we move the world to IPv6, and that's occurring rapidly. The IPX, SPX, or Novell Inter-Network Packet Exchange, IPX is actually the layer 3 protocol for it. AppleTalk and CLNS, or DECnet. You can pretty much forget these last three. IPv4, IPv6 are the predominant networking protocols at layer 3 in the world today. Now here is an important concept, and it confuses people. But IP, the Internet Protocol, as a protocol, is connectionless. There's no connection established between the two sides. There's best effort, unreliable delivery. It just sends it out there and relies on the intermediary devices to do lookups and determine where it's going to go. It's media independent, meaning it works on anything. So IP relies upon layer 4 in order to be actually connection oriented. In other words, everything at layer 3, the IP protocol, is connectionless, unguaranteed delivery. But whatever protocol the application uses at layer 4, TCP or UDP, will actually determine whether or not the protocol is connection oriented or not. So IP at layer 3, connectionless completely. It's the layer 4 protocols that determine whether or not the application is using connection-oriented or connectionless services. Now, connectionless communication is just like sending a letter, especially a non-certified letter. You don't know if the receiver's there. You don't know if the letter arrived. You don't know if the receiver read the letter. If you were going to do connection oriented, it would be more similar to sending a certified letter that has to be signed for by the individual. So, IP again, connection list. It's best effort. You route it through the network. If a packet doesn't make it to the destination, IP does absolutely nothing to retransmit. It relies upon the upper layer protocols to retransmit. And that is an important thing to realize. Media independence. This is why TCPIP took over. In the TCPIP model, we talked about the network access layer, okay? The bottom layer that is analogous to the data link and physical layers of the OSI model. When they created TCPIP, the scientists creating it did not specify layer 2 or layer 1 protocols. In other words, they said anything that comes out, we want TCPIP to be able to run on it. So it can run on copper, Ethernet, copper serial, optical, copper Ethernet again, or wireless. It can run on token ring, it can run on anything. It doesn't care as long as layer 2 of the protocol that you are writing talks to layer 3 and has the hooks to talk to the IP protocol stack. Here we have encapsulation taking place. We have our transport layer, okay, PDU, okay, our segment. You take all of this information, you package it as data at the network layer and throw an IP header on it, and that will give you your IP packet, okay. So the PDU for TCP/IP based networks, or the protocol data unit at layer 3, is called a packet. Here are the header fields that we have in IP version 4. Okay, the header for IP version 6 will be discussed in Exploration 4, but right now we're going to talk about just IP version 4 header. We have a type of service which is used a lot of time with quality of service to allow for QoS. We have fragment offsets and flags. The DF is don't fragment, MF is may fragment. The fragment offset, this is in case a packet is too big to go across the maximum transmission unit on a link in the chain. If the don't fragment bit is set, it'll be dropped. If it's may fragment, the routers can actually fragment the packets and reassemble them and send them on their way. Time to live. This is an important concept that you will not see at layer 2. In an IP packet, there is a time to live field. Every time an IP packet goes through a router, the TTL field is decremented by 1. Now, when the TTL reaches 0, it's discarded. So the TTL field is one way to help prevent loops on a layer 3 network. Because once the TTL is exceeded, it's dropped. Source address is 32-bit field in order to handle IP version 4 addresses, and destination address is 32-bit field in order to handle IP version 4. More items in the IP packet header version, which in this one's IP version 4. The header length, packet length, and header checksums. Okay, so there is actually a header checksum at layer 3, and again, you're sitting here going, well, wait, I've got error checking at layer 4, I've got error checking at layer 3 now for the header checker. I've got layer 2. Exactly, you do. That's the way it works, because remember, each layer of the OSI model does not know what is really going on above it or below it. It just talks to its peer layer on the opposite side. Okay, here's a typical packet with data. Okay, here's the header, and here's the data, depending on the size of the maximum transmission unit. Okay, so go back just a second. Time to live, okay, can be 123. That would depends on the operating system what the default TTL happens to be. Now, what are networks at layer 3? The easiest way to understand this is to think of layer 3 addresses and addressing as grouping host into logical units. Okay. To begin with, when you look at this particular network they have here, there's simply too many hosts in this network for it to operate efficiently. You wouldn't want all these on the same network. Plus, for security reasons, you would not. This server could be a student server. This could be a faculty server. This could be HR. So you want to logically separate them. Additionally, they may not be in the same geographical location. So you want to be able to say, hey, these devices are in the north office and will therefore have these logical addresses. These are in the east. These are in the West. You could do it by purpose. These are legal office computers. These are sales. These are HR. Or by ownership. Okay? So you can say public versus private. So when we start dividing our networks, we do it in order to, in some way, segment them along a logical basis. I'll give you a great example. Here at Stanley Community College, in the building I'm currently in, my PC that I'm recording this on is part of a virtual LAN, or a logical set of addresses that are totally different than any student machines. And in fact, in each one of our classrooms, we have a logical network, a VLAN, that is a set of logical addresses assigned just to that classroom, so that we know who has control of that classroom and what should be in that classroom. So we've made the decision that we're going to break our building into logical pieces by, number one, classroom, and then secondarily by role, so that we have an instructor VLAN, or an instructor logical network, that we use. Your networks will be totally dependent upon what you decide. Okay? Again, could be geographic, could be purpose, it could be ownership. Okay? And that is completely dependent upon your network. Typically you see several things. You see geographically being one, just like we do, this is the building, and inside this building we split them up. Or you see it by purpose, you know, HR computers, instructor computers versus student computers, and those types of things. This is a network, and this is a concept you need to really think about. These are broadcast and collision domains. In a network that consists of switches, okay, you have one broadcast domain. We'll learn more about switches when we talk about the data link layer of the OSI model, because they operate at the data link layer. But a switch, when it receives a broadcast, it will actually then propagate that broadcast out every single interface except for the one it came in on. So in this example, if you added, you had this network and you added a switch in the middle and added this one, you increase the size of your broadcast domain. Now, if you were to put a router in here, by the way, a router is a layer 3 device, you would end up with 2 broadcast domains, one on the left, one on the right. That way, when a broadcast occurs, only items on the left would be affected by it, only items on the right would be affected by broadcasts on that side, because by default, routers do not pass broadcasts. Now, I'm going to show you something really neat here with Packet Tracer. Inside of the Packet Tracer, the system allows you to do what are called simulation modes and runtime modes, real time. So real time and simulation. This particular Packet Tracer has 2 networks built into it, and it's a little hard to see because I know my video is down here in the corner, but there's a real time button and a simulation button. And I'm just going to click back and forth between those two a couple times, and that clears out spanning tree instances and those things. But now I'm looking at right here scenario 0. Okay, I'm going to click capture forward, and you see a PT sends out a broadcast, and watch what happens to it when it hits the switch. It goes out every port except for the one it came in on, and then everybody responds to that broadcast, and off it goes again. Okay, so this is a neat feature in Packet Tracer. It lets you show your students how traffic moves on a network. Okay, and the buffer fills up if you're not careful. Now, if I go to scenario 2, now we put a router in here. Watch what happens. It goes down, hits the switch, goes out all interfaces except the one it came in on, but it stops at the router. Okay, so the router creates 2 broadcast domains, whereas the switch creates a large broadcast domain. We'll talk more about collision domains later, but right now we need for you to understand the difference between how a router handles and works with broadcast domains versus how a switch works with broadcast domains. So again, very neat use of Packet Tracer to show a simulated environment. Make sure you show that to your students. Now, other reasons to separate our networks, we can set up iOS-based firewalls using access control list, and we can literally use routers to be firewalls. Okay, so we end up with network security in that respect. So, address management. Okay, one of the things we have to know is, how do we put IP addresses on our host? Well, there are really 2 main ways. One is DHCP, Dynamic Host Configuration Protocol. When a host boots up, and we talked about this in chapter 1, when a host boots up, it sends out a DHCP discover, it gets back a DHCP offer, it then does the host does a DHCP request from the server, and the server gives a DHCP acknowledgement. The end result is the host ends up with an IP address on the network. So that's dynamic IP address assignment. The other is static IP address assignment. So it's important that with that you just go in and you get an IP address that's not assigned to any other host. You'll assign the IP address, you assign the subnet mask, and you assign the default gateway so that it can get outside of its network. Now, this is what this slide is trying to show you. Excuse me, of all the things I've seen students have trouble with, this one is one of those things that gives them a lot of trouble. The gateway is the closest router port that is on the same logical network of your host. Okay, so it's always going to be the router port that is as close to you and on the same network. So we'll talk more about that, but what we have to do is we have to look at what the default gateway does. If you try to ping or you try to access a host that is not on your local network, okay, your machine does an ANDing process with its subnet mask to determine what network it is on. It then looks at the destination IP address and ANDs that address, and we'll talk more about ANDing in the next chapter, but ANDs that address with its subnet mask. If the two destination and source network match, it just sends it out on that network because that's a local host that it's trying to contact. If they don't match, it then sends that to its default gateway or its closest router, and that router is responsible for determining how to get it to the destination. That is how we use hierarchical addressing. Okay. Now, in our snail mail system, we use the following. A letter goes to a country, okay, US, zip code, okay, address, street address, and then finally the individual. This is a hierarchical addressing scheme. Now, I wish with IP version 4 we had followed a very strict hierarchical addressing scheme for all different parts of the world. We didn't. As a result, the internet routing table is over 300,000 routes in the core. We have done a better job at IPv6. In fact, IPv6 regions of the world have been given blocks of addresses, so we're going to be able to summarize to much smaller routing tables on the on the global network, global internet. With IPv4, though, we did use hierarchical addressing. We did that because each address has a network portion and a host portion, and some of them have an optional subnetwork portion. Okay. All IPv4 addresses are 32 bits. Okay, they consist of 4 octets. 8 times 4 is 32. Each octet is represented usually by a dotted decimal number from 0 to 255. Those numbers are used for us. The PCs and hosts are actually using binary addresses. But we're going to talk much more about this. Just realize, though, that IP addresses are in fact hierarchical. So, what does a gateway do? A gateway acts as a intermediary for a host to be able to send devices to other networks. They are layer 3 devices. Okay? So in other words, here's a host. Okay? It's trying to send something to the 3.4 network over here. So the host 230 wants to send something to 3.4. Right? Well, it would AND its address to its mask. /24 is a 255.255.255.0 subnet mask. And we get a number. In this case, it would get the network 192.168.2.0. It would then AND the destination 192.168.3.4 to its subnet mask, to the sending host subnet mask, and we get the address 192.168.3.0. Well, 192.168.2.0 is not the same network as 192.168.3.0. The host would then, if it's configured with a default gateway, send that packet over to the gateway, 192.168.2.1. It would be responsible for looking in its route tables and finding out the path to get to the 3.0 network. Now, how does it do that? Well, there's a couple ways. Well, first off, it comes in, it's destined for device on this network. If the answer is no, in other words, this host is sending something to 50, so it's not destined for the local network. It then will send it to the default gateway if one's configured. That's why when you don't configure default gateway, you can ping localhost, but you can't ping anything outside, or you can't get to anything outside. If it gets sent to the local gateway, the gateway is responsible for looking up, okay, in its route table and saying, is this a directly connected network? If no, then I need to look, do I have a route to it? If you do, or if the router does, it will then forward it to the destination. And that process takes place all the way across the router's intermediary devices until it reaches the destination network and is forwarded out by the router. So, what can we do on a host? We can go into the host and we can assign a static IP address, a static subnet mask, and a static default gateway. Just remember, this gateway must be on the same network as our host, okay? And it's the closest router port to our host. Without that, you can't get outside of your network. You can confirm those settings with an IP config. If you do an IP config/all, you get more information, but here you see that those have been set. One warning for you, I've seen sometimes when you're switching from DHCP or obtain an IP address automatically to use an IP address, you set it, you click OK, and it doesn't take effect. And you go and check it, and it's still showing 0.0.0.0. You may have to disable the interface, bring the interface back up. Not as common now with Windows 7 as it was with Windows XP. Now, what does the router do? The router, when it receives a packet from a host that needs to be forwarded, it looks in its local routing table. And the first thing it's going to do is look at all of the directly connected networks and say, are any of these the network that the destination host is on? If the answer is yes, it would send it out the interface. If not, if it has a destination network and has a next hop address, that is where it will then forward that packet. Okay? So if a request come in going to the 10.1.1.0/24 network, okay, this router would take it in on an inside interface here. Say, let's just imagine there's an Ethernet interface coming in. It would look in its route table and say, oh, okay, I know how to get to 10.1.1.0. I send that over to 192.168.1.2. And then that router is responsible to look in its local route table, and it would say, oh, 10.1.1.0, that's directly connected on my Ethernet FA00, and would forward it out. So the process is it looks through each individual entry in the route table. And we have in Exploration 2, Routing Fundamentals or Routing Protocols and Concepts, we will go over in detail how a router does a lookup. But the basic way is it takes the destination network, looks in the route table, finds the next hop address, and forwards that packet to the next hop address. Now, if the next hop address, okay, doesn't exist, okay, there's two ways that can be handled, and we'll talk about those in just a second. One is it can be dropped completely. The packet is just dropped because I don't have a destination, and a destination unreachable message is sent. Or there can be a default gateway which sends it to the next hop and then hopes the next hop has a destination. A lot of people don't know this, but actually PCs, especially Cisco and Linux boxes, have their own route table. You can actually do a netstat-r. It'll show the route table for a PC. It'll show you if the gateway's been set. Okay. You can even add to those. You can do route adds, route deletes if you want to statically assign routes to a host. If you're hacking stuff, or well, you shouldn't be, but if you're hacking stuff, this is a good way to add a route that makes things bounce through your black hat box. So here's some routing table entries. So in this particular router has a route to the 10.1.1.0 network, and it's available via 2.2, and 10.1.2.0 is also available via 2.2. And the directly connected network on FA00 is 192.168.2.0. Now here's the default route. This is a route that is a catch-all route. If you have a packet come in destined for, let's say, 172.16.10.0 network /24. Obviously it comes through and it goes, okay, 172.16.10.0 no, doesn't match this one. 72.16 no, 72 no. Well, with this route in the route table, this static default route, what happens is it says, oh, okay, anything I don't have a route for, send it over to 192.168.2.2 and then hope they have a route. Okay? At any point, if it goes up to 192.168.2.2 and there's not another static route that points it on, or if there's no route whatsoever, it will be dropped. Okay? So here's a couple next hops. Okay, so it's next hop's 2.2 and the next hop's directly connected network. So just showing you what a route table has in it. This is pretty neat because if information comes in, the router does remove the layer 2 encapsulation. In fact, this is a key point. Every single time a packet goes through a router, the layer 2 information encapsulation is removed and has to be rebuilt. Alright? Now, so it comes in, the router removes layer 2, and then looks at it, looks at the destination IP address. Okay, that's destined for 10.1.2.0. It looks in its route table and says, do I have a match for 10.1.2.0? In this case, yes, I do. Okay. It will then re-encapsulate the packet, rewrite the layer 2 information. Notice it's not rewriting layer 3. Not in this case, it's just rewriting layer 2. And then it will forward it to the next hop address. Alright. So each time a packet goes through a router, the layer 2 addressing gets rewritten, okay, as it's going through the hops. The layer 3 addressing information, the destination network is looked at, and destination IP address, and that's how you determine your next hop. If there is no route table entry, okay, so you remove layer 2, you look up the destination network, you look in the route table, there's no exact match, but there is a default route, okay, you go in and you then forward it to the default route, re-encapsulate and send it on. If there's no route at all, it comes in, the layer 2 header is removed, the destination network is looked at, the route table entries are looked at, the router says, I don't have any way to send this, to forward this to anyone else. At that point, it drops the packet, okay? And that goes into the bit bucket, and typically a destination unreachable is sent by the router back to the sending host using ICMP. That is the gist of how a routing table works. Here's another way. Here's another quick look at sharing routes. There's a couple ways you can share routes between routers. One is you can statically assign routes on all your routers. This is usually only good for routers that have only a single path out, or on networks that have very small numbers of networks on them. We also do what are called routing protocols, so that the routers can automatically tell one another about their routes and the state of those routes and those links on a router. Again, here's static routing. We configured next hop. Okay, so we're saying 192.168.2.2 is configured as the next hop for 1.1 and 1.2. And then dynamic routing, and this is how we're going to do it with routing protocols. And we have an entire semester on routing protocols that we'll talk about. Alright? That, folks, is Chapter 5 of Exploration 1. Our next chapter will be Chapter 6, dealing with actual IP addressing. Hope this has been helpful. If you have any questions, please let me know.